Today it's my pleasure to talk about machine learning and astronomy. And to be a little bit more particular, I want to tell you things we learn from learning machines. And it's just about sharing things you can do in a wrong way. So, we know it. Nowadays, astronomy is a data-rich science. Most data sets are not just big. And George, I really love your slide. I'm always using it because it's really expressing the problem we have. Everyone is talking about big data. No one really knows how to do it. Everyone thinks everyone else is doing it, so everyone else is claiming he's doing it. And for my opinion, 1 megabyte file is already big data if you don't have the right technique. I just saw a PhD student, and she was working with Excel on a file with 50,000 rows. And she was going through those rows manually because she didn't know how to program a function in Excel. And she spent a month working on this file, what would take a normal person that is familiar with TopGet something like 20 seconds. So big data is really a stupid buzzword. Nonetheless, I think we should talk about overwhelmingly large data, because that's something astronomers typically use as a word for telescope, and we are overwhelmed by the data we have.
Only at least.
Only at least, yeah. What is the US counterpart to it, George? 30 meter data, okay. So the problem is we have spatial, spectral and temporal structures in our data, and we have to deal with it. Very common are regression problems in astronomy. To be able to efficiently analyze those large catalogs, we have to solve some kind of regression problems. We really want to estimate certain kind of values. And to do it, we just have a very simple model function, whatever you would denote it, some kind of input features, input parameters, and a value your estimate will retrieve from your model. And if you want to determine those important properties, for example, like the redshift, we typically look on certain physical relations that are behind the data. And redshift is, in this example, you see two mid or high redshifted quasars from Sloan, and you see the photometric filter bands. You really have rough information on the object, but we want to recover the exact redshift of those quasars. And as you can see in this example, the one quasar is dominating the R band, the other one is dominating the I band. And for that reason, we came up with a clever idea to use colors in the past. And if you look on the images, both objects actually look really similar. But as I will show you, you can get accuracy within 1% of determining the correct redshift just based on this broadband photometric features. A very simple approach to do it, and the problem there is we cannot do a detailed analysis because it's really too expensive. So we cannot take spectra of all the objects because we don't have telescope, we don't have instrument and observation time. Because even though we are now building dedicated large telescope, a night still has just 10 to 12 hours. So we cannot observe every object with a 30-meter telescope or an extremely large telescope. So a good model to solve those problems are nearest neighbor models. There are a lot of other models, I will come to that shortly. But nearest neighbor models have several advantages. You just look on the vicinity of your objects in this high-dimensional feature space, and derive the parameter you want to estimate by averaging over the values your neighbors have. You just look around, and if you look around now, you see a lot of astronomers around you, so it's very probable that you are an astronomer as well. So, if you want to use this model, it enables you to deal with missing values. You just have to change the neighborhood function. So we have heterogeneous catalogs, therefore we might miss certain filter bands, so we switch to missing values, and then you just replace the distance function, typically it's Euclidean distance, with something where you interpolate the missing value in your distance by taking something like the average over all distances. So you say, if I don't know what is the distance in a certain filter, I just assume it's similar to the distances in all other filters I have. Very simple and straightforward approach. And now we apply this model to all quasars with spectra from Sloan. Back then it was data release 7, and what you retrieve is the spectroscopic redshift against the photometric redshift, and you can see it's more or less quite good, and you see the standard deviation is in the error of 3%, if you look on the error, so it looks somehow nice. But you always have to keep in mind, if you use certain models for machine learning, you have to know about the limitations. And in this case, and in this case, you can see if you use a local model where your reference set is limited to values between 3 and 4, you are just able to predict with this method values between 3 and 4. And what you end up is an enterprise class D, seen from the side. And if you use support vector regression, a global model, then you see you are able to predict a little bit out of your reference frame. So there are existing models. Pepe was involved in one of those papers, and yeah, they did a very nice approach by clustering in the feature space, and for each cluster in the feature space, training a support vector regression. And they had good results, and I compared them with our results, and I thought, oh yeah, we are okay, but they are much better. And then I thought, oh, what's the problem with our data set? And I figured out I didn't read the publication carefully, because I didn't have the same data they were using for the experiment. So the paper is written clearly, but I was a little bit too lazy to read all the details, and I missed some things. So I changed it, our results changed. So I did a more detailed analysis of the results and learned a little bit about the distributions. And then I read the paper again, and again. And that's really something I learned. We should not only publish the paper, we should also always publish the data set. And that's really a problem, because sometimes it's just, in this case, I was too stupid to find the right select statement that was written in there. To make it clearer, it was referred to a publication where the select statement was in. Everything was there, but I didn't get it directly, and therefore I made some mistakes. If we could find a way to make it a little bit clearer, it would help. So I read it again and again, and I figured out they were using other features than I was using. And that was challenging me, so somehow not all of the features are useful. So I have to start testing different feature combinations. And just to give you an example, what it means is, if you want to have 55 combinations by building all possible colors between the filter bands, taking the raw feature, the colors, and you just have to question what are the best 4 features out of 55 available synthetic features. Then you end up with 340,000 combinations we have to test. Back then, evaluating one model took me 100 seconds. So overall, the calculation would have taken me 400 days approximately to do this calculation. So what did I do? I improved the data set, and I thought we have to do it in parallel. So we did it on a GPU, Fabian Gieteke, and I published something on that, and as you can see, the performance is so slow in time, so fast in time, that we show the ratio, and it's in the order of 100 to speed up. So it's really fast now, and with this fast approach, we could solve it in 3 hours. So what you see here are the results of 340,000 feature combinations. For every feature combination, there is a mean absolute deviation as one measure of quality, and the root mean square error as another measure of quality. And what we can do now is, we select the star, and I can tell you, this is the worst model you ever could choose based on those features. If you take those features, those 4 features, you create really a bad model. The blue star, by the way, is denoting those features that are typically used in all the publications. So if you now go down to the Pareto front, down here, visually optimizing it, and take a model down here, you end up with this one. and it's really, really good. And compared to the other results I've shown before, the publication by Omar and Pepper, it's better. But I was challenged at the moment. I thought, oh, okay, if I now take into account more features, what happens if I put in even more? Can we even be better? So you take PSF, model petroleum magnitudes, their errors and extinction, and build a lot of combinations. So 585 features. And I want to have the best 10 out of 585 features. Just have a guess, how many combinations? Just a guess. Lots. 1.26 billion. So the last experiment I've shown you took on a GPU cluster 3 hours. Calculating all 340,000 took 3 hours. How long do you think this takes? Just a guess. It takes 3 hours if everyone on Earth has 1 million GPUs running on it. Every person on Earth has 1 million GPUs, and they are running for 3 hours, then you have the result. So it's not feasible, we really need a better strategy. That's where feature selection strategies come into play. And what we did is a greedy forward selection. What you see on the right-hand side is how the quality evolved by adding more and more features and improving model. You see it's the same plot, spectroscopic redshift against photometric or estimated redshift. And on the left-hand side you see the number of features that are slowly added. And you see, as a measure of quality, the MAD and the root mean square error. And what you see now is, we are adding successively features to improve the model, and I repeat it now again, and you see, it's improving the quality. And what I learned from it is, so, okay, we can add features. By the way, if you add more and more features, it's becoming worse. I'm not neglecting that fact, but I'm just interested in improving it, minimizing the errors. So, in the end, I came up with those features, and now Pepper and I started to struggle a little bit. And it took us a while to figure out what's the problem of those features, because those features do not look like what we expect for quasars. You have PSF max, that's what you expect for quasars. It's a point-like source. But you have petroleum and model magnitudes. Those magnitudes have been extracted for extended sources only. And the problem is, there is still, and this is showing it, improving it, and we are currently working on a publication that will be published soon, that will use those features for other experiments. You really can learn from that there is information in the image that is not well represented by the features in the catalog. And it means we are missing the faint tail of the PSF. We are not extracting what we need to do a real good task with it. And in the end, we can visualize it, and Chivo will give a marvelous talk on how to visualize those things a little bit better than just with a stupid plot. And what we learn really from that is the features we currently store in our catalogs are not thought to be used for machine learning. They are derived from measures we started with 1,000 years ago. They are meant for man to understand intensities, but it's not meant for computers. It's a simplification so we can deal easily with it. But for a computer, a high-dimensional feature space is nothing frightening. So if we take an image with a PSF and apply a PSF to that image, and we end up with just a single value, we are throwing away information. And this information is something we might want to use if we want to do certain tasks on the broadband images. And if you continue with that, this is really nice work Dennis Kübler did when he started his PhD thesis, and he was interested in supermassive black hole binaries. And back then, we were thinking about how can we find those things in spectra. And then we thought, why don't apply a nearest neighbor search on spectra? And it sounds hilarious. Why do you want to derive a spectroscopic redshift for spectra that already have a redshift? But by doing so, you can cross-check your values. And what we found is, if you take this example, it's a galaxy, overplotted is a model by Sloan, and the derived redshift. They did a chi-square minimization, fitting templates vector, and derived the redshift by shifting it. And what we did, if we just take this example here, with this line, and now you take some reference spectra, and I'm asking you to judge. So this is a reference frame, and you have one spectrum at 0.07. This one should have 0.06, 0.08, 0.12, 0.13. So what do you say, where would it be? Just by looking at it, just looking on the neighbors, you would say it's closer to those two than it is to 0.7, because the line is not here, it's over there, you see? So just simple Euclidean distance, simple comparison of spectra, because we have so many, and Sloan is really great for the majority of objects, we can use it. But it helps us to find objects where something went wrong. This object, for example, you have seen, we found has a component at 0.127. It's an overlaying component. So it has two components, it's blended, and therefore you have two redshifts. If you use a simple approach with a chi-square minimization and a template, you just find the minimum. But it's not necessarily the right solution. And you can do it for, if you look at this object, that's really a nice example how you can do it in the wrong way. Sloan found a redshift of 0.2, and it took us a while to understand why the object actually has a redshift of 0.09, because it's a certain class of galaxies with a rapid star formation process in the past. Now all heavy stars are gone, and you just have G and F stars left, and therefore it nearly looks like a star with a little bit of redshift. So in principle, by doing a chi-square minimization, you have to end up with 0.2. But by using all the data you have in your data sample, you are able to derive the real redshift of that object, under the assumption that the majority of redshift was determined correctly by Sloan. And there's another interesting object where we also have, is this the one with the arc in this here? Yeah. Where we have the arc around, that sounds to be a really disturbed object. So it really helps us to cross-validate our catalogs we have, and it helps us to detect outliers. Those objects where we have this huge deviation between the derived values. Those are defined to be outliers. Coming to the next point, so morphology of galaxies. Most of us, or I guess all of us, know about Hubble's tuning fork. And humans just come up with classification schemes to understand the world easier, to put everything in boxes, to really know how the world looks like, we have to classify. And back then, we have been challenged with galaxies from Sloan. So what did we do? We started Galaxy Zoo. We encouraged volunteers over the internet to do a certain task force to help us with visually inspecting and classifying galaxies. Nowadays, there are a lot of those examples where you do it in climate, humanities, nature, and it's still about space, astronomy. 2 years ago in Sydney, we started the Radio Galaxy Zoo project, and the Radio Galaxy Zoo project aims on looking for erupting black holes. So, what the zoo needs, the volunteers have to do is they have to mark certain, it's based on the first survey, it's radio synthesis data, and they have to fit radio contours and say how many radio contours belong to one source, how they relate to certain infrared sources, and so they have to do certain tasks. In the end, you are interested in finding triple sources, double sources, slightly elevated ones and weird ones, and you want to classify them. And the task there was limited to 200,000 objects. That was in the catalog. So we have been asked to help them analyzing the results with machine learning starting in 2014, and I completely failed. So I tried to help them analyzing the clicks by the users, doing certain things. So I had to go back to statisticians, and I asked Donald Richards from Pennsylvania State University whether he could help me with that. We got into discussion, but in the end we came to the conclusion it's probably not possible to do it with the data that was collected, because the Zoomies, the result of the Zoomies, are strongly biased. They are very incomplete because the volunteers just do a small fraction of objects, so you cannot really determine a quality out of the selections, and it just contains too many wrong classifications, at least the data we had. So what did I do? I did a very unethical experiment with a young human brain. I took my daughter Eva at the age of 2 years and did exactly the same we do. So I gave her a very simple task. Very simple, you know this brick in. And I gave her that brick and told her to put it in here. And now guess what happens. So I'm bad daddy, I know. But I told her, Eva, please put it in. And you see? You see what she's trying? My oldest daughter wouldn't have done so, but if you look on the triangular shape, it looks like a square if you look from the wrong side. So in principle it's matching somehow. And if something doesn't match a class that was given to you, and I put a strong bias on her by telling her put it in here, I was biasing her, and she recognized, oh, it's a square, it needs to fit. I took away all her potential and biased her so strongly that she could just increase the pressure to get it in, but I took away all the potential to understand what is the problem about. And so in principle, the solution is we really need now experts to inspect all the data. And we don't have enough PhD students. I don't know who made that sentence. Data is increasing exponentially. PhD students are flat. They are not increasing at all, the number of PhD students, but just with a small slope. So we really need a combination, and it's Licklider who said it, coming back to your slide. We really need a combination of the human pattern recognition capabilities with the pure data processing power of computers we have nowadays. And so we thought of using an unsupervised data processing approach, dimensionality reduction, where you take high-dimensional data. In this case, it's galaxies from the Ephibi sample from Sloan, nearby 4,500 nearby galaxies, and put them on a fixed 2D, 3D grid. So what you do is you take an image, you split it into different color channels, RGB, then you take your different color channels and slice them up, pixel by pixel, and by putting all the pixels together, you in the end up with a long, high-dimensional feature vector. And now it sounds hilarious, but you can compare images by calculating the pixel-based Euclidean distance between those images. It works somehow, but not perfect. I will come to that in a while. So you can apply, for example, principal component analysis on those long vectors and get a somehow orientation of objects in space. We published it, Oliver Kramer and I published that in 2013. You can use a lot of different methods. It works somehow. We did another trick. We sliced the image in a circular way, calculated the Fourier transform on that, because that makes it rotation invariant, but in principle it's still the pixel-based Euclidean distance. You can use isoplanar mapping. All those give you a nice result, but we still have a big problem. If we want to do it now for the radio sources accordingly, we have to be rotation and flipping invariant. And how do you make Euclidean distance rotation invariant? You do it exactly like my daughter does it. You just try all combinations. That's how we learned our models in our brain. We tried a lot of combinations, and now we know, just by looking at it, I have to turn in that direction. And so you just calculate the pixel-based Euclidean distance for all possible rotations and find the best matching angle, just by minimizing the results. And that is a very compute-intensive task, but you can do it easily on GPUs nowadays. So a very simple example, like the example I gave to my daughter. In this case, it's 5,000 images containing noisy shapes of different nature, and now you have a self-organizing map, and we will see it in action. Here, down here, you see what is the closest member in the map. And it's an iterative step. For every object here, you find the closest matching neighbor overall in the map. And then you change the map, and depending on the distance in the map, the impact of the change is becoming lower and lower. In that case, it's a Gaussian, a 2D Gaussian in the map, depending on the distance. And what you see now, if I start the training, it's evolving over time. You see it's putting it to different positions. I'm not putting anything with respect to morphology. I'm not expecting any kind of feature. I'm using pure, stupid Euclidean distance and let the map evolve. And over time, you see The map is generating and extracting all basic shapes. I'm deriving the prototypes of the data. Those are the elements that are hidden in the data, and I can jump to the end. But what you see is, you now just have to look on 25 images to definitely know what's in your data. It's boxes, it's crosses, it's triangles, it's ellipsoids. Very simple example, I know, but you take this and apply it to radio galaxies. So that's what I did. Hexagonal shape, has some advantages with the corner effect, looks a little bit more fancy, something different, and it was nice for a poster. So if you do it like that, you get a nice map representing all the morphologies you have in the radio galaxy zoo data. Very simple approach. And if you look into closer, you see you have elongated doubles with streams in between. You have a lot of different shapes in there. And now it comes to the point, it's the first time you have to ask an astronomer for assistance. Up to here, the stupid computer was doing everything. So what I did here is, I just annotated certain regions. I looked in that region and said, oh, those are boring single compact sources. I'm not really interested in those. So just by drawing this circle and donating this area to be boring, I can exclude 60% of the sources. 120,000 images. I don't have to inspect manually. It could be 120 million objects I don't have to inspect manually, because it was all done by a computer automatically. Now I have the challenging task to do the analysis of the data again. I'm not forced to go through all the images. I have the computer to do it for me. So I annotated some regions, and by doing the annotations, I now calculate something like a heat map. For every image, I calculate the Euclidean distance based to the map of prototypes I derive. Blue means very similar, red means very unsimilar. Just by looking, oh, this region is very similar, I know it's the double. Just by looking here, for this image, down here, I know it's an extended object. In that region, it's somehow extended. So I really can use it even to derive something like a likelihood to belong to one of the classes I annotated up there. Furthermore, what is more important, for those objects, for all objects, I now can calculate the distance to the nearest prototype. So this is the distance to the closest prototype. And I see from the distribution in the histogram, the majority of objects is very well represented by the derived prototype. So I extracted the right morphological information. But there is a faint tail. And this faint tail includes those objects that are not represented well by the prototype, just based on rotation invariant Euclidean distance. And those objects are the ones I want to look at. It's 1,000 objects out of 200,000. Those are the outliers scientists must be willing to look at, because those objects are really the interesting looking like. Extended ones, strange structures, strange morphology, might be artifacts or whatever, but this is the work you can do. And in principle, all the boring stuff was done by the computer, and you just do the clever stuff of interpreting the data. You can use dimensionality reduction for other things. I was asked to give a talk on a symposium for star formation, and I'm not in star formation at all. I just have basic knowledge from my studies in astronomy. So what you see is the LMC and the small Magellanic Cloud, and I thought, oh, I could calculate the star formation history for that. And I knew people spend a lot of time of fitting isochrones, determining ages of globular cluster. So I thought, okay, take some kind of globular or stellar cluster. So I took the Rigsby et al. It's 24 million stars for the large Magellanic Cloud, or 5 million stars for the small Magellanic Cloud. Yeah, that's a large one. And 24 million for the large Magellanic Cloud. So 30 million points already. Plotting them with TopCat is really easy. Plotting them with Fuse2, I guess, is still possible. So what we did is, we just took now a catalog, Beaker et al. Of stellar cluster in the Magellanic Clouds, and extracted those clouds for all objects. And then I just remember, if you do a color magnitude plot, you can somehow derive the age of a stellar cluster. So I thought, okay, color magnitude plot is nice. So I extracted a lot of color magnitude plots. one for each of the clusters. And the next step is, I cannot fit a color magnitude plot into a dimensionality reduction easily, so what I did is, I just put it into a Hess diagram with a high resolution. It's a number density plot, it's the same axis, but it's giving me a number count. And then I thought, oh, it's still too dense, I made it a little bit coarser, so I just regridded the data, and it's still keeping up some tiny variations in there, some outliers are still preserved, but it's a rough representation of it. And as I did it for a single one, I had to do it for all of the clusters. Easy work, nothing to think about, just a few minutes in Python and it around. And now we do exactly the same thing we have done with the radio galaxy zoo, but in this case we had to change the neighborhood function because the distance is now depending on number of objects that are in a stellar cluster, so you had to normalize it with the number of objects in there. And down here you see the heat map where it maps best, and over here you should see how it evolves over time. And now you see how different types of HR diagrams are sorted over time on the map, and morphology of the HR diagram is directly related to age. That's what I had in mind. So in the end, you end up, I'm skipping the movie here, you end up with a nice map. And the big question is, what is it good for? Absolutely nothing, of course, would be the perfect answer. But you just add a color for the x-axis and y-axis. And by adding a color gradient over it, you now have a distinct color for each class of objects in the plot. And if you now go back to the Magellanic Cloud and overplot those clusters, you can reconstruct the star formation history of the Magellanic Cloud without putting anything on isochrone fitting. Of course, you don't have the exact values for ages, but you see how the age distribution of the Magellanic Cloud is, and you exactly recover the result. It's going through the intergalactic material. Here it's shocking. There is starburst. They are much younger than the one on the backside. You really can reconstruct the things from the publications. And I did exactly the same for the small Magellanic Cloud, and we came to the results of the publication. So, George, you told me, try to be a little bit shorter in time, leave time for discussion. So, there we are, coming to the conclusion. The conclusion is really, try not to bias the system. Please don't do it. Just use the stupid but fast computers for the boring task, and use humans to do the creative interpretation of data. So that's really the message I want to give away. So finally, ESA gave out that picture starting this year, and they asked, is it a penguin or is it a dolphin? What's your opinion?
Penguin.
You did not listen to me. You really did not listen. It's a kingfisher. It's definitely a kingfisher. Don't be biased by a number of options. Really try to stay creative. Really try to think not to be biased. And really try not to bias others. We as astronomers really understand the world. We know what are the best photometric features because we've already used them since decades. And it took me a while really to understand what are the mistakes I made. We really know what needs to be in a database, but we learn what is in the database is not correct. And Dennis will have a really nice example on features where we know they are perfect, but in principle they are completely bullshit and don't make any sense. And we are biased in so many things because astronomy is so old that we really have to get rid of those biases and start to think more creative. Be open-minded for a lot of new approaches. Some of those new approaches can be completely bullshit. Yes. But if we are just bound by our history on things we do, we cannot perform the task we should do. So, thanks for your attention.